All right, so in Schoology, you will see that I did supply you with the pH concept notes if you want them, but otherwise you can take your own notes. But again, we're dealing with pH concept today. All right. So before we get to the pH itself, we have to understand the basis behind it. And the basis of the pH world starts with understanding the autoionization of water. Okay, so water is the classic amphiprotic substance, and we haven't used that word very much, but essentially amphiprotic means it's a substance that can act both as a Bronsted-Lowry acid and as a Bronsted-Lowry base, right? Which of course means sometimes it can donate a proton and sometimes it can accept a proton. All right, so when you talk about in water, just water sitting there, both of those things can happen at the same time, both donation and accepting. And so therefore you end up with autoionization. It takes care of ionization all by itself. So if you think about it this way, we have two water molecules, right? And one of them is going to take and donate its proton to the other. And so when you do that, you end up with a hydroxide ion and a hydronium ion. Okay, so if we sort of keep these things as left and right, this one has donated a proton, so that means that's our acid. This one has accepted a proton, so that means it is a base. And on the other side, we of course get our conjugate base and our conjugate acid. So autoionization happens in water, in any water, pure water that's just sitting around. Okay. And this is an equilibrium. And so as a result of that, you can write the equilibrium expression for this particular thing. So again, we don't put liquids into our equilibrium expression, so we end up with a equilibrium expression that looks like this. Concentration of H3O times concentration of OH minus. We give this particular equilibrium constant a special name. We give it the name Kw. And so therefore Kw equals the concentration of the hydronium ion times the hydroxide ion, or remember, hydronium and hydrogen are interchangeable, so the concentration of the hydrogen ion and the hydroxide ion. Right, so that equilibrium constant, Kw, like any equilibrium constant, is temperature dependent. Okay, and so an important temperature for us to remember for Kw is 25 degrees Celsius, standard conditions. And so if that's a particular case that we have here, at 25 degrees Celsius, Kw has a value of 1 times 10 to the negative 14th. Okay, but we know that autoionization is an endothermic process. Okay, that we can measure that. And so if we were to rewrite the equilibrium expression, we might end up with an expression that looks like this, right? It's endothermic, so put heat on the left. And so using what we learned about K's previously, if I go ahead and I increase the heat, the reaction is going to shift to the right, okay, in order to bring the heat back down or the temperature back down. And so that means that our concentrations of H3O and OH are going to go up, which means that Kw is going to go up. Likewise, if we decrease the temperature, it's going to shift this reaction to the left, and you end up with a situation where Kw is going to go down, and so it decreases. Okay, so again, as temperature increases, Kw increases. As temperature decreases, Kw decreases. And over here, we just have some data to show that. All right, so when a solution is neutral, your concentration of H3O plus and OH minus are the same, right? You have the same amount of acid as you do base, and so that puts us in neutral categories. If we go back to that special case that we were talking about at standard conditions, Kw equals 1 times 10 to the negative 14th. So if that's the case, if we think about that, that means that this is X and that's X, and so as a result of that, in a neutral solution, you end up with these being equal and the concentration of both of them being 1 times 10 to the negative 7th molar. Okay, as temperature increases, the concentration of those two, of course, is going to be greater than 1 times 10 to the negative 7th. As temperature decreases, it would be less than 1 times 10 to the negative 7th. All right, so this brings us to the concept of pH. Okay, and so for pH, we assume that we are dealing with that special case of pure water at 25 degrees. All right, so we're going to assume that it's 1 times 10 to the negative 7th molar. Now you'll notice that's a really, really small number. So in any regular solution, most of the water molecules stay as H2O. A very small percentage go to H3O plus and OH minus, right? What percentage? Well, 1 times 10 to the negative 7th molar, which is a really, really small percent. Okay, so in order to avoid having to deal with small powers of 10, they developed the pH scale. The pH scale is based on logarithms. And so pH equals negative log of the concentration of the hydronium atom. All right, so if we are dealing with that special situation at 25 degrees Celsius in a neutral solution, the concentration of both of those is 1 times 10 to the negative 7th. So therefore, in pure water, we know that the pH equals the negative log of 1 times 10 to the negative 7th, or 7. So this, of course, is where we end up with a neutral solution has a pH of 7. All right, so from there, we know that acids have a higher H3O plus concentration than pure water by definition. All right, and so that means that this number is going to get -6, -5, -4, etc. So the pH ends up being less than 7. So acids have pHs of less than 7. Likewise, a base is going to have a lower H3O plus than pure water because H3O plus and OH minus are related to one another. So as a result of that, in a base, the pH ends up being greater than 7. Table down here summarizing that both in terms of concentrations and in terms of the pH. So once we understand that, we can broaden this idea of this P symbol here, meaning the negative log of any number. So we can broaden that out to OH. We can broaden that out to KW. So pH is the negative log of H. POH is the negative log of OH. PKW would be the negative log of the KW. If we put those together, we can get a fairly useful expression because at that standard condition, we know that the concentrations of the two ions combined is equal to KW, which is 1 times 10 to the negative 14th. So that means PKW is 14. Okay, and we know that from that, if we go negative log of H3O plus using logarithm rules, negative log of OH minus will give us the negative log of KW, which equals 14. Or in other words, the pH plus the POH equals PKW or equals 14. Okay, so that's a useful expression. pH plus POH equals 14. Okay, so once again, this reminds us to go back. That statement we just made that pH plus POH equals 15 only applies at 25 degrees Celsius. At other temperatures, the value must be different, so neutral pH may be greater or less than 7. So the big takeaway, and the takeaway we want to always do, is that neutral doesn't always mean a pH of 7. Neutral means that the concentration of H3O plus and OH minus are equal. Okay, and so you will see that as the temperature goes down, pH goes up, and as the temperature goes up, pH goes down for neutral solutions. All right, last piece of this that we need to deal with is measuring pH. Just how do we know what the pH of something is? Well, we have gone ahead and we've developed some pH meters. These are based on electrochemistry. And so in the redox reactions, to be able to figure out what the pH is from that. We also use indicators. Sometimes an indicator is a solution we add to a acid or base, or sometimes it's embedded on a piece of paper that we add to an acid or base. So in other words, when we measure pH, we use a pH meter or an indicator.